Hi there. In this video, I'm going to talk about phosphoric acid. Something that's always kind of interested me was that when you did a titration of phosphoric acid, it's something that I do in a lot of my labs, or my teaching labs, that we only ever see 2 of the 3 equivalence points. Technically, there are supposed to be 3 equivalence points, right? When you react an acid, the hydrogens react really one at a time, right? So with H3PO4, we transfer 1 hydrogen. And if we add just 1 equivalent of hydroxide, that's going to consume 1 of the 3 hydrogens that this triprotic acid has. And so it forms H2PO4 and a water molecule. Then if you keep adding a second equivalent of hydroxide ion, that's going to transfer another of the remaining 2 hydrogens off of H2PO4 onto that. We get HPO4 and another water molecule. And finally, if we keep adding a third equivalent of hydroxide to this, then off of the HPO4, we should get with hydroxide ion, we'll get the phosphate ion and H2O. Overall, if you add all of these equations together, this is what we would typically see if you did this back in Gen Chem 1. You'd have 3 equivalents of hydroxide reacting with the H3PO4. You get PO4 3- and 3 equivalents of water with that. That would be your overall reaction. So in theory, we should be able to see each of those. Here's the issue with equivalence points. We typically only see them on a graph if there's a big enough change in the pH. And it's that third equivalence point that I've never been able to find before. So I decided to set out in the lab and see if I could figure out a way to actually see that third equivalence point. And what I ended up doing, here's the graph that I ended up with. I ended up trying to minimize the volume of the solution. I figured out that it was that the concentrations with a regular titration were just so dilute, especially when you used a relatively small concentration of base. The concentrations were so dilute that it was just a smooth line up here. And you can see it's pretty smooth in this case. But I want to show you a little bit of detail with that. What I ended up doing was titrating with drops of sodium hydroxide. So again, that's how I minimized the volume. So there was very little volume change, just measuring the pH. So each one of these is a real data point I used with my pH meter after each drop. So you can see here, there's only, what have I got? 1, 2, 3, 4, 5, 6, 7. There's about 30 or 40 drops of NaOH that I added to make this particular titration curve. And so you can see the first 2 equivalence points are completely obvious. There's one right here. All right. And that's where that first hydrogen has completely come off. All right. Over here, we start with H3PO4. Remember, this tells the story of this titration. And so if we start with this strong acid, as we add base to that, it begins to strip off that H3PO4. So then we go through a buffer solution that contains the original acid H3PO4 with some of its conjugate H2PO4 minus. All right, that's this buffer section here. That's why the pH is relatively flat through there. Buffers buffer the pH. They keep the pH from changing a lot. So I had this buffer solution. But when you run out of H3PO4, that's when there's a big change in the pH. And that's what happens right here at that first equivalence point, is all you have is that H2PO4 only substance. All right. Then we go into a second buffer. As we continue to add more sodium hydroxide into this, we get a second buffer system, H2PO4 minus and HPO4. We get a mixture of those 2 ions in solution. It creates another buffer solution. So again, we have this buffer solution through that section there. What am I going to be left with right here at this next equivalence point? Well, there it's just the HPO4 2- ion that remains. All right, and then we go into another buffer section. Now you can already see, though, here after this this next equivalence point, HPO4, the pH jumps up to 12. All right, we're into another buffer section here of HPO4 2-, and what's the other substance? PO4 3-. Again, we just keep taking those hydrogens off one at a time. All right, and so this is the key point. Do you see right there? There's a little tiny equivalence point. There's just the almost imperceptible jump in the pH right there. All right, and so that's that third equivalence point right there. You can see it. And that's where phosphate ion, PO43 minus, is the only thing affecting the pH. It turns out the HPO4-PO4 buffer and the phosphate ion pH are very, very similar. That's why there's just not that big jump in pH, unlike what we have down here between the H2 HPO4 buffer and HPO4 minus. There's a couple of pH unit difference there. And so that's why we see that one. We just don't see that with phosphate ion. And then after that, if we continue to add more base to this, then your strong base, the NaOH, just kind of takes over everything. Well, again, the pH of that NaOH is very similar to the pH of the phosphate ion. And so we don't see a huge jump in the pH there, just a little tiny bit. But you can see that third equivalence point is there. All right, so that's the story of this particular titration. There are 3 equivalence points. It's just that third one is very, very difficult to see. All right, here's another way you can see that. What I did was I plotted a derivative plot on top of this. What a derivative plot shows is the change in the pH from one data point to the next. So in a buffer section, there's not much change. And so there's not much that you see with that derivative plot. When you hit an equivalence point, like through here though, there's big jumps in the pH. All right. And so that's why there's a big peak there in that derivative plot that you see in the light blue color. Then we go into another buffer where there's not much change in pH. Then we hit another equivalence point, big spike there. All right. And then we get another buffer where there's not much change, but look at right there. And that's what confirms that right in here is that other third equivalence point. Again, there's not much, but it's definitely there. You can see that little bit of a jump in the pH, not as big as the other two, but it's definitely there with that. So there is a third equivalence point for phosphoric acid. It's just there's not much difference in pH between the buffer, the phosphate ion, and the sodium hydroxide. And so if your concentrations are all dilute enough, it just kind of blends from one right into the other. But if you can keep those concentrations in your dilution low enough, you can see that, particular solution in there. All right, so like I said, this was with drops, and you can see they happen right where we would expect them to be. In this case, the first one happened at 7 drops. So the second one we would expect to happen around twice that much. So 2 times 7 would be 14. I got it at 15 drops in this particular case. Again, it didn't come out perfectly with a data point. So it probably was between the 14th and 15th data point in that case. And where did the third one come out? It should be 3 times that first one. And it came right at 21 drops. So you can see it works out perfectly at 7, really 14, and then 21. I'm using real data with this. All right. I didn't make this up. I didn't draw this on a computer. I mean, I used a computer to draw my data, but it's real experimental data with this. All right. You can try this yourself. This is what we do in science. See if you can do that same thing. And so here, just to kind of reiterate, I actually went through and did the calculations for these. And so for a 0.1 molar H2PO4 solution, just to get us approximate pHs of that would be about 4.7. That corresponds to that data point right around in there. All right. Then if I had a 50-50 mix of H2 and HPO4, the pH there would be 6.2. That would also be what's called PK, the pKa of H2PO4. Turns out that's pKa2 for phosphoric acid. That comes right in there. All right, be right in the center, kind of the midpoint between these 2 equivalence points. Then if all I had was HPO4, that would be right in there, 9.8 for that one. Again, this goes with what I was just saying before, but take a look at what happens on these last 3 calculations here. For 12.4, that would be the pH right at a 50-50 mix of HPPO4 3-. And so that's going to be right about in there. And then the pH of phosphate ion, a 0.1 molar phosphate, is going to be 12.6. Again, that's what we're seeing right about in there. So again, just barely a change in pH from 12.4 to 12.6 in that case. And then if you had a 0.1 molar sodium hydroxide, pH would be about 13, which is what you're going to see about up in here somewhere. All right. And so that's what's happening with that phosphoric acid. Technically, there are 3 equivalence points. It's just really difficult to see that third one. All right. I don't think anyone's ever shown that before, at least that I was able to find. So maybe somebody did a long time ago and I haven't done a literature search on that, but But that's what you can see with the titration of phosphoric acid. Again, I was really excited when I saw this titration curve there. So kind of neat to see, you know, not everything has to be, you know, brand new or groundbreaking, but it's stuff I hadn't seen, at least on the internet before, as far as that. And most everybody just says, oh, you only see two. Well, you can see the third one. It's just really difficult to get it this way. All right. So anyway, I thought that was neat. I'll see you in the next video.